Reference beam method for determining thermal fluctuation constants. Thermal fluctuation constants of the generalized Gorokhov equation are currently determined on the basis of experimentally obtained data of the dependence of durability from stress and temperature by a graphical analytical method. This method is based on rearranging the experimentally obtained graph into the graph with coordinates of the logarithm of durability versus stress, log, and into a graph of the dependence of the logarithm of durability versus inverse temperature, log, 10^100/t. Two constants Lg-0 and T are found from the position of the pole, and the other two U and, from the graph of the dependence of the activation energy on stress. This method of determining the thermal fluctuation constants is rather complicated, and the need to perform graphical rearrangements reduces the accuracy of the results. The established linear dependence of the change in the constant log-0 on the magnitude of the pole displacement along the ordinate, Fig 1a. The change in the thermal fluctuation constant U also has a linear dependence on the magnitude of the displacement of the beam pole only along the abscissa axis, Fig 1b. The obtained dependences, along with other regularities due to the thermal fluctuation nature of fracture and deformation of solids, Fig 1c, d, e, make it possible to propose a reference beam method for determining the thermal fluctuation constants of the generalized Gorokhov equation. The proposed method does not imply rearranging the experimentally obtained graph. Its principle is based on manipulation with a reference beam. For experimental verification of the hypothesis, polyvinyl chloride plates were chosen as the object of the study. This choice is due to the fact that it has a homogeneous structure and the presence of temperature-time force equivalence of the destruction process is clearly traced for it. To identify the temperature-time force equivalence, beam samples were made of polyvinyl chloride. The total number of samples was 150 pieces. The length of the samples was 6 cs. The cross-section is rectangular, BH equals 1. 5 cs 0. 3 cs. For transverse bending and fracture tests, a 6-position stand was used. Thermal fluctuation constants for the reference beam were obtained on the basis of experimentally determined constants of PEC plates at transverse bending, log-0 equals -2. 34 equals 43. 85 kg/mol MPa T at 437. 95 K U equals 313. 85 kg/mol. The beam with the coordinates of the pole point 10 and 11 was taken as the reference beam I. E. Log equals -1, equals 10 MPa and the maximum temperature possible T at equals 500 K. To determine the thermal fluctuation constants by the reference beam method, a system of coefficients is used, K. It seems possible to determine the structural mechanical constant, and the value of the activation energy of destruction U on the basis of the ratio of the angular coefficients of the reference and the desired beam, expressed by the coefficient K. To check the developed technique, let us determine the thermal fluctuation constants of the generalized Gorokhov equation for a decorative protective slab based on a polyester resin binder using the reference beam method and compare the obtained values with the constants for this material obtained by the graphic and graphic analytical method. Experimental data are presented in table. On the basis of the experimentally obtained data, Table 2, a graph of direct temperatures in the coordinates Lg, for a decorative protective board on a binder made of polyester resin was built. The limiting temperature of the existence of the material is determined from the linear dependence of the change in the slope of direct temperatures, shown in screen. The values of the coefficients K and K are correspondingly equal. Let us determine the thermal fluctuation constants U and, for a decorative protective board based on a polyester resin binder, U equals. The obtained values coincide with the results obtained by graphic and graphic analytical methods and presented in table. Analysis of table shows a high convergence of the results of calculations performed by the graphical analytical method and by the method of the reference beam, which indicates the adequacy of the proposed method for determining the thermal fluctuation constants. Thus, the technique of the reference beam makes it possible to determine the durability of the material according to the generalized Gorokhov formula without additional plotting in the coordinates t, 10/t, and u, which reduces labor intensity, and also, more importantly, avoids errors that arise in the process of graphic constructions.